This video is about logic in mathematics. So the world of mathematics is a lot larger than making computations. A major theme in the subject of mathematics is furthering mathematical theory. That often takes the form of devising and proving new mathematical theorems. So that's work that didn't just happen hundreds of years ago. It's something that is ongoing and active to this day. In this course, I'm hoping that you'll learn a little bit about what it means to state and prove and apply mathematical theorems. So we sort of begin that process here in this section, where we're going to learn about the meanings of these words: theorem, proof, definition. These are important words in mathematical theory. And to give you an example of where some of these words are used, I've provided on this slide a page from an abstract algebra book where you see some of these words. For instance, we see the word definition, where we're learning the exact meaning of a particular word. In this case, we're learning what it means for a permutation, whatever that is, to be even or odd. We also see the word theorem, right, which is a statement, a true statement. And then below it, very important word is the word proof, where we provide an argument that that statement is true. Over the next few slides, we'll unpack some of the words that commonly occur in mathematical theory. So the first word we're going to talk about is definition. And the meaning of a definition in mathematics is maybe a little bit different from what it means to the rest of the world. So in math, the purpose of a definition is to give the exact meaning of a particular term. And here there are three examples that I've provided. The first one from geometry is the definition of a circle. Right? It's a plane figure consisting of all points that are equidistant from a given point. That tells us exactly what a circle is. And in the second two bullet points, we describe what it means for an integer to be odd or even. So an integer is odd, essentially, if it is a multiple of 2 plus 1, and it's even if it's a multiple of 2. Now, there are other sorts of definitions that occur in the rest of the world that are not quite what we mean by a mathematical definition. Like, for instance, I pulled off this definition of supernatural fiction, which doesn't tell us exactly what it is. It's merely descriptive. And while it's a useful description, it doesn't serve to define exactly what supernatural fiction is, whereas a mathematical definition should tell us exactly the meaning of the given word. So you can sort of translate the idea of a definition to formal logic in this way, right? Definition statements often have the form for all x in a certain domain, d of x, if and only if p of x, where d of x is the predicate describing the defined term, like, say, circle or odd or even, and p of x is like the collection of properties that characterize the term, such as being equidistant from a given point or being a multiple of 2. So, at any rate, what you might notice is that the symbol involved in the formal logic interpretation of a definition is the symbol for if and only if, right? We want circle, the notion of a circle, to be equivalent to the notion of being equidistant from a given point. So you might wonder, well, why don't we use the words if and only if in a definition, right? Like in the second and third bullet points, we only see the word if. We don't see the words if and only if. And the reason for that is that it's just simply convention to leave off the and only if in order to save space. So the if and only if is implied. It's not stated, but it is implied, and I want you to be aware of that. So an axiom is an object that is crucial and in fact foundational for any mathematical theory. An axiom is a statement that is assumed to be true and is used possibly together with other axioms to form the basis for a mathematical theory. So you can think about an axiom as sort of a beginning for a mathematical theory. Theory must begin somewhere, and it begins with these fundamental assumptions that are regarded as being true by reasonable people. So a great example of a collection of axioms are the axioms of Euclidean planar geometry. So all of the theory of Euclidean planar geometry comes more or less from these 5 axioms. All of the results you're familiar with, like the Pythagorean theorem, or the fact that the sum of the interior angles of a triangle adds to 2 right angles, all of those things sort of spring from these assumptions. So let's go through these assumptions, right? So the first says that a straight line can be drawn from any point to any other point. Second, finite straight line can be extended continuously. And third, a circle can be formed with any center and radius. So axioms 1, 2, and 3 are certainly reasonable because we know about straight edges and compass, right? If you have a straight edge, you can undertake axioms 1 and 2, and if you have a compass, you can undertake axiom 3. Axiom 4 tells us that all right angles, like this one and that one, are equal to one another, meaning that I can take one, pick it up, and lay it atop the other exactly. And then you have this rather curious axiom 5, which I have managed to misstate a little bit here. I should also say here that the point A is not on L. So given a point A and a straight line L, with A not being on L, there is exactly one line through A that does not intersect L. So this is sort of a complicated axiom, which is known as Playfair's axiom, and it's equivalent to what's known as the parallel postulate. And this sort of seems a little bit different from the first 4 in the sense that the first 4 seem manifestly obvious, whereas the 5th axiom or assumption you have to sort of think about a little bit and may not be manifestly obvious. So a theorem is both a building block and an end product in a theory of mathematics. So a theorem is a true statement that can be inferred from axioms or from other previously established theorems. So on the previous slide, we had the axioms from Euclidean geometry, and on this slide, we have some examples of theorems that occur in Euclidean geometry. So the very first example is sort of interesting. It is the very first theorem in Book 1 of Euclid's Elements. So it's the very first theorem that follows these axioms. Okay, and it says that an equilateral triangle can be constructed on any line segment. Now, it might be interesting for you to pause the video and go back and look at the axioms and see if you can come up with an argument involving those axioms that will allow you to infer this statement. Okay, so the next example is an example I mentioned on the previous slide, and this is Book 1, Proposition 32. So it's the 32nd theorem in Book 1 that follows those axioms. It says the sum of the interior angles of any triangle is 2 right angles. And then finally, our final example is Proposition, 47, I guess. And it says in a right triangle, the sum of the square on the hypotenuse is the sum of the squares on the other two sides. So we would recognize this last bullet as being the Pythagorean, or at least one part of the Pythagorean theorem. Now, it turns out that if you change the axioms, then the theorems will change too. For example, if we were to look in spherical geometry, where the last axiom, axiom 5, in Euclidean geometry, that is the parallel postulate, if we take that away and replace it with something else, then we get different theorems. In fact, in spherical geometry, we get triangles where the interior angles can sum to 3 right angles. So a theorem is no good without a proof. So a proof is a convincing argument demonstrating the truth of a theorem. So a proof is based on axioms, definitions, and previously established theorems. So as a model, it's helpful to think about propositional logic, which we discussed a few days ago, right? We want to be sure to play by certain rules to make sure that our arguments are convincing. Now, a lot of theorems can be codified in terms of, symbolic logic. Like, for instance, there exists an x such that p of x is true. Or for all x, p of x is true. Or for all x, if p of x, then q of x. So we're going to see a lot of theorems in mathematics have, one of these 3 forms. Well, a claim is a statement that aspires to be a theorem. Now, if it is a true statement and we can show that it's true, then it becomes a theorem. Otherwise, it's a false statement and it becomes nothing, right? So if you have a claim of the form for all x, px, showing that the negation is true, that is, there exists x such that not p of x is true, that's called finding a counterexample to this particular claim, and it will show that the claim is false. So for example, we have this claim, all odd positive integers are prime. That is a claim that has this form. And we're going to show it's false by finding a counterexample. So this is false because 9 is an odd positive integer. And 9 is not prime. So we finished these slides by exploring the words definition, theorem, proof, and axiom in the context of 4-point geometry. So 4-point geometry, like any mathematical theory, needs to begin with some axioms. So here we have 4 axioms, and they all involve words, of course, and there are some words that are going to be undefined terms at this juncture, such as point, line, and is on. And maybe that surprises you that we're not going to define those terms, but in reality, we can't define every single word, right, that we use. This is true in Euclidean geometry as well, So there are some words that we just have to accept. Now, what do our axioms say? Well, if we have 2 distinct points, then there's a unique line such that both points are on that given line. Second, if L is a line and X is a point not on L, then there's a unique line M such that X is on M and no point of L is on M. Third, there are exactly 4 points, hence the name 4-point geometry. And finally, it's impossible for 3 points to be on the same line. So at this point, you might be tempted to draw a picture, and I encourage you to do that. So maybe you'll want to go away now and draw a picture. Okay, I'm assuming you've paused the video, drawn a picture, and come back. Probably your picture looks a little something like this, right? From past experience, we have an idea about what a point should be, and we're told from our axioms that there are exactly 4 points. So let's let those be our 4 points. And then I know that between each 2 points, we have a line. And I know, or there's a line such that for any 2 distinct points, each of those points is on that line. So I might draw something like this based on my past experience with lines. And I can't forget these lines here. So my picture might look something like this. And then you might wonder, well, what do we make of this central thing? It looks sort of like like an intersection, but apparently not, because there are only 4 points. Now, a picture is a good thing, but an argument, like if we're going to prove a theorem in 4-point geometry, a proof of a theorem should not depend on a picture. A picture can be used for motivation, but the theorem proof needs to depend on axioms or on previously established theorems. So on the previous slide, we casually talked about the idea of intersection in this 4-point geometry. So now we're going to make a definition. We're going to define what it means for 2 lines to intersect. And here again, you might pause the video and try and write down a definition for intersection. Okay, so I assume you've been away and maybe have written down something. So, I don't know, maybe what you wrote down looks something like this. So if we have 2 lines, L and M, intersect, if there is a point X such that X is on L and X is on M. Right? So maybe that looks a little something like the definition that you produced. And it tells us exactly what it means for 2 lines to intersect. Okay, here we're going to prove a theorem in 4-point geometry. So the theorem is that there are at least 6 lines in 4-point geometry. And if you go back and you think about the picture we drew, this theorem makes some sense. Now, it's not enough for us just to draw a picture. We want to produce an argument that convinces people beyond a doubt that there are at least 6 lines. So let's go ahead and do that. So the first thing is we know that by axiom 3, there are 4 points, and let's label them I don't know, A, B, C, and D. So we can use these to form 6 distinct sets of 2 points. And so here they are. Right, so there's A, B, A, C, A, D, BC, BD, and CD. Now, so given any 2 distinct points, there's a unique line such that each of those points is on that line. So use axiom 1. To produce 6 corresponding lines. Now, at this point, we might think that we're done with the proof, right? But there's one more thing that we have to be careful about, and that is we want to show that there are at least 6 distinct lines, right? The implication is that these lines are distinct, right? We don't want any repetition. So why is it that none of these 2 lines can be the same line? Well, let's suppose two of these lines were identical. Then there would be at least 3 points on that line. So these lines are distinct. As otherwise, there would be 3 points on a given line. Like, for instance, suppose the line corresponding to pair AB is the same as the line corresponding to pair AC. Then points A, B, and C would all be on the same line, and that's impossible by axiom 4. So, therefore, the lines are distinct, as otherwise axiom 4 is violated. So that is a proof of this theorem. And now if you had gone away without seeing this and made your own proof, it might look a little bit different from the one that I've written down, and that's perfectly okay. But the key elements of the proof would be, I'm quite sure, very similar. You would need to start with axiom 3 to get your 4 points. Right, so what are the common elements of every reasonable proof of this theorem? You would have to start with axiom 3 to get your 4 points. Then you would have to form a set of 6 pairs of points, and then axiom 1 would have to come into play to form 6 lines from those pairs of points. And then in your argument that those 6 lines are actually distinct, you would have to invoke axiom 4. And probably the most common error in a failed attempt to prove this theorem would be failing to remember to show that the lines are distinct. That is, failing to invoke axiom 4 in your argument.